Hello everyone, welcome to my channel. Please like and subscribe. In this video, we'll be learning how to design a beam for double reinforced section. Double reinforced section, the reinforcements are provided in both tension and compression zones. The region of tension zones provided at the bottom of the section, like in this way, at the bottom of the sections, where is tension reinforcement are provided, and the region of compression zones is the region found at the top of the section. This is the region of compression zones. Okay, now let's see our problem. A rectangular beam is simply supported over a span of 6 meters and carries characteristics dead load including self-weight of 12.7 kN per meter and imposed load of 6 kN per meter. Like in this way, since the beam is simply supported, it have two spans which have a span of 6 meters. 6 meters carries dead load including self-weight. So this is dead load, which was 12.7 kN per meter, and carries imposed load. The load added at the dead load, which was imposed load, which was 6.0 kN per meter. The beam is 300 wide, so this is the wide of the beam. The wide of the beam, which is 200 millimeter, and the effective depth of the beam is 300. Effective depth is the depth from the center of the tensile steel up to the top of the section. So this is effective depth. Effective depth was 300 millimeter. And the inset of the compression steel means that the effective depth of compression steel was, this is effective depth of compression steel, which was 40 millimeter. And we have given we are going to design the beam at midspan at maximum moment of this beam. So we have given concrete grade, which is SU is 30 Newton per millimeter square, and reinforcement grade, which is FY, is 460 Newton per millimeter square. Now, let's design step by step this rectangular beam for double reinforced section, as there are various steps to be followed. Now, step number 1 is to find the design load. Design load is per BS 8110 part 1, 1997. Design load is given by this formula: 1.4 times dead load plus 1.6 times imposed load. We have given this is dead load and imposed load is this one. So we substitute in our equation. So design load will be equal to 1.4 times 12.7 plus 1.6 times imposed load, which is 6.0. So when we compute this equation, it will be equal to 1.4 times 12.7 plus 1.6 times 6. It will be equal to 27.38 This is kilonewton per meter. This is the design load to be used in our designing of the beam. As the next step is to determine the maximum design moment, which acts at the center of this span of the beam. So, maximum design moment. We find maximum design moment. Maximum design moment. Maximum design moment is given by this formula. Design load times L square over 8. So it will be equal to 27.38 times span, which is 6 square divided by 8. So it will be equal to times 6 square divided by 8. It will be equal to 123.21 kilonewton meter. Therefore, maximum design moment is 123.21 kilonewton meter. The next step is to find the ultimate moment of resistance. Ultimate moment of resistance. Ultimate moment of resistance. MR. Ultimate moment of resistance is given by this formula 0.156 SU times BD square. Now let's substitute. We have SU, which is 30 Newton per millimeter square, times BD, which is 200, and we have effective depth, which is 300. Now let's substitute into our ultimate moment of resistance. It will be equal to 0.156 times Fc, which is 30, times B, which is 200, times effective depth, which is 300 square. So this is Su, B, and the depths, effective depths are in a millimeter square, are in a millimeter. So to convert into meter, we multiply by power negative 6. So it will be in kilonewton meter. Now, ultimate moment of resistance, when we compute this one, it will be equal to 0.156 times 200 times 300 square times exponent negative 6. It will be equal to 0.156 times 30 times 200 times 300 square times exponent negative 6. It will be equal to 84.24 kilonewton meter. This is ultimate moment of resistance. So in order to determine our design is for double reinforced section or single reinforced section, is to check and compare. Does maximum design moment is greater than ultimate moment of resistance? In our calculation, we have obtained maximum design moment, which is 123.21 kilonewton meter. This is greater than ultimate moment of resistance, which is 84.24. So this is greater than 84.24 kilonewton meter. So since maximum design moment is greater than ultimate moment of resistance, double reinforcement and tension reinforcement are required. Therefore, we design as a double reinforced section. We design as a double reinforced section. Means that both compression compression and tension reinforcements and tension reinforcements are required. Are required. Now, the next step is to find the area. Since both compression and tension reinforcement are required, it will be required to determine the area of compression steel and the area of tension steel. Now, first of all, let's find the area of compression steel. The next step is to find area of compression steel. Area of compression steel. Area of compression steel A dash, which is given by this formula. Maximum design moment over 0.95 Fy times effective depth minus effective depth of compression. Before finding this as the area of compression steel, it will be required to determine to find the value of Z, so as to determine that the area of compression steel is so as to determine the compression is yielded or not. Fy is used when this Fy is used direct, which was provided in our question, if the compression steel only is yielded. If it's not yielded, there is formula to be used. Okay. First of all, let's find the value of Z, which is given by this formula: 0.5 plus 0.25 minus k dash over 0.9 under root. This should be less than or equal to 0.95 times effective depth, but this k dash is equal to 0.156. Okay, now let's substitute into our equation. It will be equal to 0.5 plus 0.25 minus k dash, which is equal to 0.156 divided by 0.9 under root. This should be less than or equal to 0.95 times effective depth. Now, let's compute this one. 0.25 minus 0.156 over 0.9 and root of answer plus 0.5. Okay, it will be equal to 0.78 times effective depth. This is less than 0.95D. So we take, since it is less than, so we take 0.78 times effective depth. Therefore, Z, it will be equal to 0.78 times effective depth. Our effective depth we were given, which was 300. So we multiply by 300. So effective depth, it will be equal to 0.78 times 300. It will be equal to 234. This is millimeter. Okay. Now let's check. Does the compression is still yielded or not? Check for yielded steel. For yielded steel. If the compression is yielded, this effective depth of compression over x should be less than or equal to 0.37. But this x is equal to effective depth minus z over 0.45. Now x will be equal to effective depth is 300 minus z, which is equal to 234 over 0.45. Therefore, x will be equal to 300 minus divided by 0.45. It will be equal to, x will be equal to 146.67. This is millimeter. Now, let's find effective depths at compression zones divided by x. Effective depths at compression zones, it was 40 millimeters. So we take 40 millimeter divided by 46.67. It will be equal to, divided by ounce, it will be equal to 0.27. So effective depths at compression zones of over x is equal to 0.27. This is less than 0.37. Hence, the compression still is yielded. Since it is yielded, now we use Fy directly into this equation so as to determine the area of compression, which is given by this formula, 0.95 Fy times effective depths at compression zones. Now, let's substitute. Maximum design moment is 123.21 kilonewton meter. So to be in Newton millimeter, so we multiply by 10 power 6 over 0.95 times Fy. Fy is this one, 460. So we multiply by 460 times effective depth, which is 300 minus effective depth at compression zone, which is 40 millimeter. So we minus by 40. So the area of compression, it will be equal to, now let's compute this one. 123.21 exponent 6 divided by 0.95 times 460. 300 minus 40, it will be equal to, no, the area of compression, since it is used when since from this case, for Doubly in first section used when ultimate moment, maximum design moment is greater than m1, which is the ultimate moment of resistance, which is m is greater than, since m is greater than m1, so to obtain the area of compression, so we take maximum design moment minus ultimate moment of resistance. Even at this, we minus by ultimate moment of resistance. So ultimate moment of resistance 123.21 exponent 6 minus ultimate moment of resistance was 84.24 kilonewton meter. So 84 we minus by 84.24 exponent 6. Now let's compute this one. It will be equal to 13.21 x.6 minus 84.24 x.6 divided by 0.95 times 46 300 minus 40. It will be equal to 342 minus 0.99 millimeter square. Now, to determine, as the next step is to determine the number of bars required at the area at the compression steel. No, we know for beam bar diameter is from 16 millimeter, 20 millimeter, 25 millimeter. Now, you know, for one bars is equal to pi times bar diameter square over 4. Let's assume we use minimum bar diameter, which is 16 millimeters, so it will be equal to pi 16 millimeter square divided by 4. It will be equal to 20.06. Now, this is the area of one bars. Okay, to determine bars required at the compression, it is obtained by taking this area of compression, which is 342.99 divided by 201.06. It will be equal to 1.7. So for economical, normally we round into the whole number. So bars required, it will be equal to 2 with a diameter of 16. Therefore, the compression steel, to determine the area required. Area required is this one at compression. So to determine the area provided at compression is obtained by taking the number of bars, which is 2 times the area of one bars, which is 201.06. It will be equal to 402 millimeter square. Therefore, the compression steel provides two bars with a diameter of 16 millimeter, which provides the area of compression, which is 402 millimeter square. The next step is to determine the area of tension, since the designing of double reinforced section involves both the area of compression and the area of tension. Now, the area of tension. Yes, area of tension is given by this formula over 0.95 Fyz plus area of compression. Therefore, area, it will be equal to ultimate moment of resistance is 84.24 x.6 over 0.95 times Fy, which is 4, 6 times Z. Z is 234 plus area of compression. Area of compression is this one, is 342.99 0.99. Therefore, area of tension will be equal to 84.24 exponent 6 divided by 0.95 times 460 times 2 times 2 times 234 plus 342.99. It will be equal to 1166.79 millimeter square. Now, the next step is to determine the number of bars required. Let's assume the main bus is 16 millimeter, which is the minimum bar for beam. Now, the area of one bar is equal to, by using the diameter of this one, which is equal to pi times 16 square over 4, it will be equal to 20.06 millimeter square. So, bars required, it will be equal to 1166.7 divided by 201.06. It will be equal to 6 bars. Therefore, bars required, it will be equal to 6 with a diameter of 16 millimeter. To determine the area, this is the area of tensile required. To determine the area of tensile provided is obtained by taking number of bars, which is 6 times the area of one bar, which is 201.06. It will be equal to 201 times 6. It will be equal to 1206 millimeter square. Therefore, the tension steel provides 6 bars with diameter of 16, which provides the area of tension of 1206 millimeter square. Now, the next step is to draw the detailing for the section of the beam. Detailing of reinforcement. Detail of reinforcement. The section of the beam was in this way. Number of bars of tension is 6. So tension still are provided at the bottom. So we provide the number of bars 6. 3, 4, 5, 6. This is a 6 bars with diameter of 16, which gives the area of 206 millimeter. Okay. For double reinforced section, we have the reinforcement of compression, which is provided at the top of the section. The compression steel was provided. It was 2 bars provided at the top, so it will be equal to 2 bars. 2 bars. This is 2 with a diameter of 16, which gives the area of compression, which is equal to 402 millimeter square. As this is the distance from the center of the compression zone to the top, is effective depth of compression, which was 40. And this is effective depth, which is 300. Now this is the detailing of the section of the beam. Thank you for watching this video. Please like and subscribe for more civil engineering tutorials.